Hi, welcome back to Unit 1 here in AP Physics C Mechanics. This is topic 1.3. This is representing motion, right? And so, again, a lot of this stuff is not much different than what we talked about last year or what you talked about in the mechanics course. The difference will be, that we will introduce in non-constant accelerations, right? So motion can be represented in different ways, right? Diagrams, figures, graphs, equations, narrative descriptions. The most common ones that we use here in physics are going to be graphs and equations, okay? Motion diagrams will show up every once in a while. That's the series of dots that's separated by, that are put down every time, separated by a time difference. That actually translates into data tables. Then ultimately those data tables will translate into graphs, okay? Now, last year, right? Again, we assumed constant acceleration, and so, or in an algebra-based course, we call these cake constant acceleration kinematics equations. Again, so this makes the assumption that acceleration is constant, and that's when we end up with the graphs that have parabola, line, right, slope line, and then a horizontal line for acceleration. Now, what happens here in physics C is that you'll get a stack of graphs that looks like you see here on the screen. So typically your position function will be cubic, then your speed function, right, will be parabolic in some way. Then your acceleration will be linear, right, a slope line. And then you introduce in this concept known as jerk, right? So jerk is what creates a non-constant acceleration. Okay. And that's more real world, right? So we know that acceleration, like if we drive a car, we know the acceleration is not constant, right? Unless you put on your cruise control, which actually creates constant velocity, which means there is no acceleration. But over time, actually, if you hit certain parts of the road, that that cruise control will actually shift. It'll accelerate or have a positive acceleration, negative acceleration, if you need to speed up or slow down, if you go over what you set it at. Okay. Now in this one, we're talking about that the special case, right, of what happens when we are near the surface of Earth, right? We get that vertical acceleration caused by gravity, which is going to be downward and constant with a measured value of 9.8. Or you can just simply use 10, right? Multiple choice questions, 10 will probably be the one that you want to use, but 9.8 will probably be the one that you use in free response questions. But you also have to make sure, what does the test want? Sometimes it'll say use G equal to 9.8. If it doesn't make that statement, then you can use 10, okay? And then you can see here graphs of position, velocity, and acceleration as functions of time can be used to find the relationship between these quantities. Well, if it's constant acceleration, there are your graphs, those two equations. But if it's non-constant acceleration, like I said, you'll see what is over here on the side. All right, so let's look at an example problem of representing motion. Okay. So here we have a large cat running at a constant velocity of 5 meters per second in the positive x direction. It runs past a small dog that is initially at rest. Just as the cat passes the dog begins accelerating at 0.5 meters per second squared. That should be a superscript, not a 2, in the positive x direction. Okay. How much time passes before the dog catches up to the cat? How far has the dog traveled at this point? And then how fast is the dog traveling at this point? Okay, so here's where we're going to actually do some, potentially do some, we could do vector notation, right? But notice that both of these are going to be running in the positive x direction. So what we need to do is write the equation for each one. So generally, we will start with our displacement equation. Okay, and we will fit our our information to this. So the dog or the cat has a constant velocity, so it has no acceleration, and it is going at 5 meters per second. The dog has no initial velocity, and it is traveling at 0.5 meters per second squared. That is, sorry, our acceleration. So his function becomes, or their function becomes 0.25, right? So how much time passes before the dog catches up to the cat? Well, we set these equal to each other because at that time they're at the same position. Sorry, I wrote a 0.5, not a 0.25. Right, and then we solve this. Right, don't necessarily, just as a heads up, don't cross out factors of t right now because you actually do lose a data point. Right, so recommendation: subtract that 5t over, and then you can treat it as a quadratic formula. Well, all right, so I factor out a t. Well, that gives me 2 times t equals 0. Well, that's where they start. And the other time would be at 0.25t minus 5 when that equals 0. And then we just solve this for t, right? And it'll take 20 seconds for the dog to catch up, right? Or until it passes the cat. All right, so now how far has the dog traveled at this point? Okay, well, we know this position is the same point, right? The same location. So you can use either equation, right? So I'm going to use the cat. Why am I going to use the cat? Because it's just 5 times t, right? So I don't necessarily need a calculator to figure out 5 times 20. I know that's 100 meters. But if you don't believe me, do 0.5 t squared or 0.25 t squared. You get 20 squared, and you end up with 100 because 20 squared is 400. A quarter of 400 is 100, right? So there's our answer to part B. Now, how fast is the dog traveling at this point? Well, we use our velocity equation, v equals VO plus AT. We know they have no initial velocity. And so we just simply do A times T or 0.5 times 20. And they're moving at 10 meters per second at this point. Okay, so this is a little bit easy because we've got them, one direction, right? They're both traveling in positive x direction. In the next video, we're going to talk about frames of reference and relative motion. So what happens, essentially, maybe what happens to the cat and the dog when they're traveling kind of in horizontal, vertical directions.